Georgios, the floor is yours.
Thank you, Ricard. Hi, all. My name is Georgios Katsikas. I also work with UBITECH. This is a joint work with Kostas Poulakakis, Pantelis Malekas, and Nikos Karamanolakis. And it speaks about zero-touch onboarding and adaptation of P4 data planes leveraging in-band network telemetry. Why this is important? Deep network telemetry is a key enabler, in our opinion, for AI native 6G, simply because AI needs the data, and this is what we provide in this demo and presentation. And how we are attempting to do that, we try to combine different open source projects and standards, with most of them being around for several years, and with TeraFlowSDN being in the center of attention. Specifically, TeraFlow, Stratum, SD Fabric, and P4. What is the objective? We would like to close the loop because this is what automation promises in general, and it's important for 6G. So this zero-touch service and network management, or the ZSM concept, applies actually here because we would like to use the in-band telemetry data, which provides real-time monitoring of the network state, as an enabler for AI to make smart decisions, so be intelligent, and then close the loop with automation. At a high level, what is the challenge in the ecosystem of TFS? Well, this ecosystem has multiple layers. So at the bottom, you see the network infrastructure, for example, and then we have multiple layers within TFS, which interact with infrastructure. The immediate layer is the device layer. Here we have drivers which speak some configuration protocols to the devices, but also we have monitoring daemons which try to collect the network state. On top, we try to build end-to-end services. And on top of that, we have the management layer where we try to make decisions. This is where we employ policy components, automation components, and stuff like that. And on the side, there's a data layer which goes vertically. So all of those layers produce some data, some control or data plane stuff. We need to exploit this data and try to close the loop. So it's a space with multiple layers of abstraction, which we need to take care of. What projects are behind this activity? It's two projects, Across and FlexScale. For Across, we have been speaking a lot about automation and zero-touch operations. There are specific test cases in Across which have to do with zero-touch onboarding of P4 devices, zero-touch provisioning of in-band network telemetry on those devices, and also real-time network adaptation using this data. And for FlexScale, there's a whole part of the architecture which speaks about ZSM and how we close loop with policies. And this goes also in the optical layer, which is not something that we will talk today about, but has to do with FlexScale. Now, why this is relevant for TFS? Well, on the left-hand side, you see what are the new features that are introduced by this work today. And on the right-hand side, you see the relevant open source projects and standards where we try to align and contribute. I'll briefly mention those. So we have introduced some bug fixes in the P4 SBI driver of TFS with this work. 3 new P4 services for layer 2 forwarding, layer 3 routing, static routing, and in-band network telemetry. We have extended the Mininet open source software stack with support for not only native Stratum switches, which was done by ONF already, but now for INT-based Stratum switches. This is a work by UBITECH. We have a new telemetry backend collector in TFS, in the new monitoring system of TFS, which is getting those INT data and reports those data. This new collector is based on an open INT specification produced by the P4 applications group. And we have a revised automation component, which is now able to introduce custom ZSM plugins, we call them, or closed loops, and to prove to prove this feature, we have implementation of a specific ZSM plugin for our case, for a P4 data plane and INT data. And finally, we have extended the policy component to support some service level operations to close the loop, like the update service RPC. Something that I didn't mention previously is that the work we have been doing here in the P4 world about not only the driver but also the services is fully aligned with SD Fabric. So we have imported the P4 implementation of SD Fabric in TFS. And those three services that we provide today are based on SD Fabric data plane. Why now? So actually, it's a good opportunity today to test the new telemetry subsystem of TFS. This was introduced back in November in the release 4, and at the ETSI SNS for SNS event in France in November, we managed to have a joint proof of concept with other people in the room, with UOP and CTTC, which was basically using this INT driver at the service at the device level. Since November, we have been doing the work in the service level. So we introduced the new service handlers for INT and other SD Fabric services, and we have implemented the new TFS collector for INT data. This is going into release 5, and now it's the best timing basically to test this whole end-to-end system and see it as a whole. And attention here is that this is a kind of still of work in progress. We will release this work as an experimental feature now in release 5. We encourage the community to use it and report any potential bugs to us so we can fix things. And this work will be stabilized in release 6, basically. The team behind the POC is Kostas Poulakakis, myself, Pantelis Malekas, and Nikos Psaromanolakis, as I said previously. Some background into INT, In-band Network Telemetry, before we start. What is INT? It's basically a framework designed to allow the collection and reporting of network state by the switches, by the data plane directly, so without involving the control plane. How this is done, there are 3 ways according to the recent INT specifications by the P4 community. It's the export data, embed instructions, and embed data. I will not go through painful details for those. There is the material here to read upon, but long story short, we use the first way, the export data. I will show you exactly how it works. It's a scheme where every switch reports INT packets to the collector, and the original packets are not modified. How this is done? Let's assume that we have this topology with 3 switches and some hosts around. This is the SDN controller and the collector, which we place it here as an external component, but now it is part of TFS. To start the INT, the collector needs to tell the switches which are the flows we are interested to collect INT data from. So it basically releases a flow watch list to the switches. When a switch matches a packet which belongs to this flow list, it knows that it needs to report data to the collector about this packet. So a new packet is generated by the switch, and it's sent to the collector. This packet contains telemetry information about switch A. The same happens for switch B, as the original packet traverses the network, and same goes for switch C. So finally, the collector has aggregated state from 3 switches as the packet traverses the network. The initial packet is not modified, but the collector has information about this flow in the system. And now I will go into the steps of this little demonstration. We have employed a virtual testbed, meaning that we have 2 VMs. One VM acts as a TFS controller, another VM where we deploy Mininet with the Stratum-enabled P4 switches. Step 0 is to provision the system. So we start with the provisioning of TFS itself. TFS, in our case, is a set of components, which you can see here: context, device, telemetry, the KPI system, analytics, service, path computation, automation, policy, web UI. A key here is that now with our new INT collector, the telemetry service in Kubernetes uses a load balancer IP. This is important because this is a kind of an exposed endpoint of the collector for the switches to be able to send the telemetry data, because the switches are in a different VM, they're remotely somehow. So we need to expose this new endpoint in the TFS Kubernetes system for anybody else outside to be able to send telemetry data there. And we used Metal LB behind that. Second step is to provision the TFS. It's the same step. Basically, when we provision the TFS, this is what gets created in the VM. So a set of components inside Kubernetes. And then the second follow-up operation is to provision the topology underneath. We go to the other VM, we start Mininet, and we instruct Mininet here to use Stratum BMV2 suites with INT capabilities. This is a new class that we created in Mininet. The difference here is that each switch with INT capabilities has one more network interface, which contacts the INT collector on the north side. We have done this in the open source repository of Mininet. An open point here that we can discuss also as part of TFS is maybe to upload this whole Mininet repository in TFS so that other people can use it and experiment with this. Okay, now the topology is bootstrapped. This is the topology that we use, a client server and 5 switches in between. Here we use these purple dots to indicate the in-band network telemetry interfaces of each switch. This is the dedicated interfaces they use to send INT data to the collector. And the gray ones are for the configuration. So the P4 runtime gRPC server exposed by Stratum. Next, we need to onboard the topology. So there's a JSON file which we upload on the web UI, and this, when uploaded, stores the new topology in context and instructs the SBI to connect with the switches. Once this is done, each switch gets a new P4 program to execute, but there's no forwarding logic yet in the data plane, so nothing works at the moment. Once we upload the JSON, this is the look of the topology on the web UI of TFS. It's basically the same figure I showed earlier. And if we look at the configuration of each device, we see that every device is bootstrapped and it carries some basic initial rules for the configuration of the device. These rules do not include any data plane forwarding logic yet. In the second step, we need to provision a new P4 INT service. Another JSON is uploaded on the UI as a first step, and the web UI then knows that it needs to contact the service component of TFS. This is where we develop the service handler for P4 INT. Once this is done, the service initiates a new INT collector. This is part of the service logic. So it contacts the telemetry component to start a new job, a new thread, which attaches to this load balancer IP that I told you earlier in Metal LB, waiting for INT packets to arrive from the switches. And this complies to the P4 INT spec v0.5 that I told you previously. In the third step, the same service handler now talks to the SBI, to the device driver, to insert rules to the switches to be able to do the INT reporting. So every switch now gets those rules, and if any packet goes through, now they will be able to send telemetry data to the controller. Second step, or third step after this, is to create a layer 2 service, because as I told you, there's no forwarding logic yet. If you try to ping from client to server, it's not going to work because the switch doesn't know how to do the forwarding. We do this in step 3. We upload another JSON, which we call service layer 2, on the web UI. This again contacts the service component, but now triggers a different handler, the handler that does the layer 2 forwarding. When this is done, the service component asks the path computation for a path between the client and the server, gets the path back, and then configures the driver with rules to actually realize the path. So eventually you see that we create this new yellow path between client and server that goes from switch 1 to switch 5 via switch 2. So we take the north part of the topology. This is the initial provisioning of the forwarding logic. Now, if we go into the service tab of TeraFlow, we see that we have these two new services. One is layer 2, and the other one is the INT. And if we go to the devices tab, we see that 3 switches, switch 1, 2, and 5, as I told you previously, have additional rules. These are the rules installed for layer 2 and in-band telemetry. So in the fourth step, then we try to send some traffic. So we go into the mininet and we try client ping server. This basically instructs packets to go through the north path, as I showed earlier, and the ping works. When this is happening, though, there is some effect. As the packet traverses switch 1, 2, and 5, these 3 switches report data to the telemetry collector as the packets go through. So the collector gets those packets and gets the network state immediately. In the third substep here, the telemetry component reports those INT data into Kafka. So actual KPIs are created in the TeraFlow system. These KPIs are pulled from Prometheus, the basic telemetry database of TFS, and the same happens from Grafana. So we see actually the INT data in Grafana of TeraFlow. And this is the look of it. When we started the ping at this point in time, we see immediately that the switches report their hop latency into the collector, and this gets visualized in Grafana. So we have hop latencies for 3 switches here. Now we have the system ready. We have all the provisioning of the services, INT and layer 2. We have a working client to server communication, and we want to create a ZSM loop on top. So how this is going to happen? Again, another JSON, the automation JSON now, goes to the web UI to create a ZSM loop. Let's see what the automation needs for this. The automation needs to know what is the service that requires this ZSM loop. For us, this service is the layer 2 service, the one which does the forwarding. We input this up here. So in the starting point of the automation JSON file. But we also input here the same service ID into the policy component, because the policy is going to be used as a means from automation to do the actuation on the service. Next, we need to tell automation what is the input here. So based on what data, it's going to automate something. And for us, the automation inputs here in this specific case are the hop latencies of the 5 switches that we are pushing to Grafana and to Prometheus. So every switch out of the 5 create those hop latencies and send them to Prometheus and to Grafana. And we are going to create an automation loop using this as an input. This is an input to the analyzer component of TeraFlow, which is going to produce an output, a new KPI. It takes the 5 latencies, and out of those which are not 0, because not all of the switches do the actual forwarding every time. I told you previously that traffic goes from client to server from switch 1, 2, and 5. So switches 3 and 4 are not used in this case. So their KPIs will be 0 in this case, their latencies. So the analyzer is able to detect only the active switches, those that report some latency, gets the latency metrics from those switches, and produces a total one-way latency, new KPI, which is basically the one-way latency from the client to the server. This is an output KPI that we are now going to use as a means to trigger a policy. So if this latency exceeds some threshold, which we define also in the analyzer, then we use the policy component to enforce an action, an actuation. And this actuation goes through the service component to perform a reconfiguration in the service, meaning, for example, a change of path. So all this information goes through the web UI to the automation component, and then automation first creates an analyzer to take these inputs data and produce a new KPI. This new KPI is now immediately pushed into Kafka as well. So we have it also in Prometheus. And we create a policy, automation creates a policy based on this new KPI. So now the system, the automation loop is ready to do the job. It just needs data to trigger itself. Because the policy also subscribes to Kafka and waits for an alarm. So the alarm here says that is triggered when the new KPI exceeds the threshold in Kafka. So in step 6, we try to artificially introduce some delay, or artificially or physically actually, introduce some delay into the path so that we are able to trigger the policy. This means that the moment that this happens, that we basically introduce this delay, INT data is collected in telemetry. The threshold exceeds in Kafka, and Kafka throws an alarm to the policy component. When the policy component gets this alarm, it contacts the service component to update the service. Service asks for a new path with some constraint from path computation. So it tells that we shouldn't go through switch 3 now because there's a delay there. The path is congested. And path computation returns a new path for the service. When this is done, the service goes to the driver and changes the forwarding behavior. So instead of the yellow path previously, which goes through switch 2, now we reserve the green path, which goes through switch 3. And this is how we manage to close the loop. So again, as I said, this is a work in progress. We haven't really concluded to the full extent what we are trying to achieve here. There is future work and sets of improvements that we foresee already. First of all, we would like to stabilize a little bit the telemetry system and improve the performance. We have observed some delay for the data to reach Grafana, actually, which we need to take a look on. It could be just a matter of simple configuration. We have seen some issues in the management of constraints in path computation component of TFS, which we would like to solve. And we also foresee some new features in other components of this POC, specifically the analyzer, to be able to manipulate multiple KPIs at the same time and do some math operations on top of those KPIs, like add KPIs, subtract, multiply, divide, and so on. And of course, we would like to take this whole work into the quality of service world, especially in P4, because the new SD Fabric support that we introduced in TFS also offers quality of service characteristics, which we would like to exploit. And of course, try to test this not only in Mininet, but also with the Tofino hardware switches. So that's all, actually. Thank you for listening. Any questions you may have? Happy to answer. Yes? Yeah.
So that one example that you actually have input KPIs and you have an aggregated output KPI that you evaluate for the route. Right?
Correct.
I guess a simpler version could be, is it supported that you can have a single input KPI that is also the output one?
Correct, it is. This is what it was actually developed initially by CDTC.
Okay.
But we wanted to actually take the analyzer into the next step and try to, combine KPIs together. It is possible what you say, though, yeah. But we wanted to have the whole latency path, the whole latency view. So this is why we did this add operation there. Yeah. Mm-hmm. Mm-hmm.
How it works? I mean, every packet that transit switches sends a packet.
Yes, so when you instruct the switch with telemetry rules, you tell the switch what flows you want it to match. So, for example, you have ICMP traffic from client to server, and you want telemetry only for this ICMP traffic. You send a telemetry rule to the switch which says, if you match ICMP traffic, I want you to create a telemetry packet for me. So when the ping goes to the switch, it matches, this is an ICMP, the switch creates a new UDP packet, which is empty in the beginning. It puts source IP and port of the switch, destination IP and port of the collector, and creates a new header on top of UDP, which is called INT header, and there adds all the possible metrics that the switch can basically report, which are hop latency, queue occupancy, some bandwidth related metrics and stuff like that. So all these things are put inside the INT packet, and this goes to the collector. Yes, for every packet that traverses, a new UDP packet is generated and sent. Yeah, that's a very well-known problem. Well, yeah, there has been a lot of work how to scale the collector, actually, to be able to match, to perform well when you inject a lot of traffic, or to do some cherry picking of packets instead of getting every packet. There's a whole bunch of research work how to scale this. Bloom filters is the way. There is a way to do Bloom filters in the P4 switches and selectively send telemetry data to the collector. Yeah, this is what the Bloom filters do, yes. There has been a lot of research work around this. There could be also open implementations of Bloom filters in P4. Another piece of work could be kind of DPDKA enabled collector to be fast and take packets in the user space very quickly, or BPF stuff there.
That was my question.
Yeah, XDP. Yeah.
If we need to have a plan inside TeraFlow for EVPF,
Yeah. That could be an early POC to attempt, but this is only for the collection side. eBPF can also be seen as a driver of TFS to configure the switches with eBPF. Yeah.
So that's one.
Yeah.
Okay.
Affected depending on how packets.
We haven't done an evaluation of this POC, but this work was initially done in collaboration with the Warsaw University of Technology. We have two colleagues there, Jakub and Tomek, who did some joint work with us in the context of the master thesis of Jakub. There, they actually reported stuff like that. So they did a performance evaluation on the switches and the collector to see what is the impact of telemetry in the data plane and also in the control plane. I can send you the thesis of the guy. It's a very well-written thesis report with an extensive evaluation. There they used Tofino, actually. So on the data plane, Tofino doesn't really bother. It can send as much as you want, but the collector is the problem. So yeah, I can send you the report of the thesis.